Okay, now that we've had our now we've had our review of partial fraction, um, uh, basically, decomposing them into partial fractions. Let's go ahead and put it into our integral problems. And we have, let's do something like, let's turn that into a cubed. Let's do 2x cubed plus x squared minus x dx. Okay. Now we know, well, and it may actually be easier to go ahead and pull this aside, okay, like this, in order to just do the decomposition and then go back to the integral, okay? And so what we have here is we have a over x plus b over x plus 1 plus c over 2x minus 1. Okay. Well, when I multiply through, and this is going to be linear factors, so it's going to wind up being a wonderful convenient value, or Hebesid method. Bx 2x minus 1 plus cx x plus 1. And all we've done again is just multiply through by the common denominator in order to get rid of the denominators and canceled out, the things that cancel out. And so let's say if x is equal to 0, then of course nothing happens to the left side since there's no x to actually plug in for. The left side's always going to be 0. And we wind up getting a times 1 times negative 1, so a is equal to negative 1. If x is equal to negative 1, then these two go away, okay, and we're left with b times negative 1 times negative 3, or b is equal to 1/3. And if x is equal to 1/2, which would get rid of the 2x minus 1, then 1 is equal to c times 1/2 times 3/2, and so c winds up being equal to 4/3. Well, that means that the integral of dx over 2x cubed plus x squared minus x is actually equal to negative 1 over x plus 1/3 over x plus 1 plus 4/3 over 2x minus 1. And with the exception of finagling a little bit with the coefficients, that winds up being just 3 natural log integrals. Okay, so this winds up being negative dx over x plus 1/3 dx over x plus 1 plus 2/3, because I have to leave a 2 behind in order for the numerator to be the derivative of the denominator. And this is negative natural log absolute value of x plus 1/3 natural log of x plus 1 plus 2/3 natural log of 2x minus 1. And of course you can combine those according to properties of logarithms, and you're going to need to go ahead and practice that, because on the AP exam it won't likely be in this form. It'll likely be in the combined form using properties of logarithms. But for our purposes right here, it's not to review properties of logarithms, but to basically show you how the decomposition into partial fractions, just being the work done right here, takes the original and turns it into something that can be integrated very easily with respect to natural logs. Now, of course, if it's going to be linear factors in the denominator, linear non-repeating factors in the denominator, you're going to wind up getting all natural logs, right? Now, if they're repeated factors or if they're irreducible quadratics, that's a different story, okay? And let's go ahead and get to a repeated factor here, okay? Let's go ahead and do x squared plus 12x minus 5 over x plus 1 squared x minus 7 dx. Now, I need to go ahead and remind you that when you're doing decomp, you need to remember that in order to do decomp and to get the actual correct answer, you need to make sure that that the numerator is of a smaller degree. Now, it doesn't happen very often, but if the numerator is the same degree or a higher degree, you actually have to do division before you do the decomp. Here, it doesn't really matter because the denominator is of a higher degree, the numerator is of a smaller degree, and therefore we can just go ahead and do it like this. Now, when we multiply through by the common denominator, we're going to wind up getting a times x plus 1 times x minus 7 plus b times x minus 7 plus c times x plus 1 squared. Okay. Now we can go ahead and we're going to use the convenient value method or the Hevesed method at some point. I would rather go ahead and do it after I sort of do the multiplying out and the recombination in terms of coefficient comparison. So that's ax squared minus 6ax minus 7a plus bx minus 7b plus cx squared plus 2cx plus c. I wind up getting a plus c x squared. Negative 6a plus b plus 2c x plus negative 7a minus 7b plus c. Now remember, not all of these are actually going to be needed because two of these I'm actually going to wind up dealing with in terms of the Hevesed method. So if x is equal to 7, now when x is equal to 7, let's go back up to this line right here. This term, now there are three terms right here, right? If with x is equal to 7, the first two terms go bye-bye. And the only thing I'm left with is this third term. So let's figure out what x is equal to 7 does to this side. Now, 7 squared is obviously going to be 49. 7 times 12 is, of course, and if you're forgetting how to do arithmetic in your head, that's 7 times 10 plus 7 times 2, which of course is 84. So we have 49 plus 84, which is 133. 133 minus 5 is 128. Okay, and then c times 8 squared. So c is equal to 2. Gosh, didn't that work out nicely? Because, 128 divided by 64 is 2. Let's go ahead and do if x is equal to negative 1. Now, if x is equal to negative 1, that's 1 minus 17. So that's negative 16. Okay, and of course, that's going to make this term and this term go bye-bye, and you're going to wind up getting b times negative 8, or b is equal to 2. Okay, so let's go ahead and that's 1x squared plus 12x minus 5 is equal to a plus 2x squared plus negative 6a plus, well, that's going to be 2 and 4, so that's plus 6x plus negative 7a, and that's going to be negative 14 plus 2, so minus 12. Well, you don't even have to go that far, because if a plus 2 is equal to 1, then a is equal to negative 1. I have my three values. Okay? So my integral of x squared plus 12x minus 5 over x plus 1 squared x minus 7 dx actually gets transformed into negative 1 over x plus 1 plus 2 over x plus 1 squared plus a 2 over x minus 7 dx. Natural log, power rule, natural log, right? Because this winds up being dx over x plus 1 plus 2 times x plus 1 to the negative 2 dx plus 2 times the integral of dx over x minus 7. Okay? And of course, you can do this on your own. I'm just sort of running out of room right here. But basically, if you have a repeated factor, it winds up being the undoing of the power rule. Okay? So, non-repeating linears become natural log. Repeating linears become power rule. Well, let's look at one that has a irreducible quadratic in it. Okay? How about 3x plus 5 over x squared plus 4x plus 13. Well, here's the thing. You actually don't even have to do the decomp on this one. You can't do the decomp because the denominator doesn't factor. In fact, the denominator doesn't even have any solutions, okay? Remember how you can look at it and tell this is the perfect square trinomial moved up 9 units. 9 units. That's kind of interesting. Okay, so we see the fact that this, if I wanted this to be natural log, just straight natural log, I would need 2x plus 4 in the numerator, or some multiple thereof. Okay, so what I need to do is figure out how I can change this. Well, if it's 2x plus 4, then 3x plus 6 will actually work, okay? So can I transform this from 3x plus 5 into 3x plus 6 minus 1 over x squared plus 4x plus 13 dx? Well, that allows me, okay, to pull it apart, separate the fractions, like this. Now, you might be thinking, why is that a step forward? Well, let's go ahead and transform this, okay? And once I do, I know that I have 3 halves times 2x plus 4 dx over x squared plus 4x plus 13. Well, that's all well and good. I've done a really good job of transforming this first integral into something that is integrable. What about the second one? Well, here's the thing. If I actually use, completing the square, the same process that we use to turn something into vertex form, I can transform that denominator like this. Okay? Well, I can further transform that denominator by multiplying through by 1/9 over 1/9. Okay, and I'm just going to sort of leave this one here. And so what I have here is I have 1/9 dx over x plus 4 over 3 squared plus 1. Now that's looking a little bit more favorable. That kind of looks like arctan. Okay? And it actually is. I only need, however, one of those 1/3. That's 1/3 squared. So what I'm going to do is I'm going to bring one of them out, leave the other one in that numerator, and I have something which is going to, let's go and leave that as a negative, going to turn into arctan of x plus 4 over 3. And of course this one right here is 3 halves natural log, and you don't have to use, since there's no solutions and it's always positive, you don't have to use the absolute value bars, plus c. Now, I wish I didn't have to do this every time. I wish there was actually a formula that would allow me to sort of shortcut. Oh my gosh, there is. Okay, and if you want to memorize it, I'm the kind of person that wants to actually do the process. I'd like to do it the long way because formulas, like I've said before, are easy to forget. But if I have the integral of du over u squared plus a squared, where u is my expression in terms of x, and my a is my constant, okay? this winds up being 1 over a arctan u over a plus c. Isn't that what we got right here? Identify this 9 as 3 squared, and once I've designated that as 3 squared, it's 1 over 3 arctan u, which is x plus 4, over 3 plus c. Okay? So when I have an irreducible quadratic, I need to figure out a way to transform it, if I can, into arctan. So non-repeating linears become natural log. Repeating linears become undoing the power rule. Irreducible quadratics become arctan, okay? And it's just a matter of pulling these things apart when you can, and upon pulling them apart, changing the form such that you can actually identify what's going on and integrate them appropriately. Let's go ahead and call it quits for this particular video. We'll probably do one more in terms of this, since y'all are pretty conversant on decomp and the integration. It's just a matter of bringing them together. So we'll do another couple of examples in the next video, and then we'll move on to the rest of what ails you for this next test. As always, if you have any questions, please do email me. Bye.